Good morning. My name is Yann Falevoz. I'm in charge of Collaboration Chip Management and Tech Marketing at UPMEM, and I'm pleased to welcome you to the second edition of ABUMPIMP, the symposium dedicated to the applications and benefits of UPMEM processing in memory technology. Let's start with a brief overview of UPMEM. UPMEM was founded in 2015 with the aim of providing a solution to the data and energy bottleneck of compute-centric architectures. Indeed, in the case of data-intensive applications, such architectures reach their limits with communication between the main memory and the CPU happening through a narrow bus with limited bandwidth, high latency, and most of the energy in the compute node related to DRAM data movement. The solution for this is to integrate powerful compute capacity into the DRAM memory die, that is PIM-DRAM. There are several ways to do so. At the beginning, in the 90s, processing in memory consisted in putting classical memory and logics into the same chip without changing the memory structure. But technology evolved, and the logic progressively integrated the memory structure either in its periphery or in the memory array. It was then necessary to introduce new terms to distinguish those technologies. Thus, one referred to near-memory computing and in-memory computing. UPMEM technology falls in the first category and is the first PIM architecture to be commercialized in real hardware. While in-memory computing products are now available on the market, they inherently offer lower memory density, limiting their use mainly to edge applications. We sold our first server in 2020, and since then we have proven the capacity of the technology to speed up and reduce the cost and energy of a large number of applications compared to CPU, GPU, and FPGA. But let me explain the technology in more detail. An UPMEM PIM server is a standard Xeon x86 application server where most of the DIMM slots have been populated with PIM DIMMs. Standard and PIM DIMMs coexist in the server, and the firmware is made aware of the specific configuration. A typical configuration totalizes 20 PIM modules. A module takes the form of a standard DDR4 2400 DIMM, embedding 16 PIM chips for a capacity of 8 GB. Chips are produced using DRAM processes without manufacturing implication. Inside each chip, 8 processors coexist, and we call those processors DPU, standing for data processing units. You probably done the math. A typical configuration totalizes 2,560 DPUs for 160 GB of PIM DRAM. A DPU is a simple modern general-purpose processor. It shares the access with the host CPU to a DRAM bank called main RAM. Instruction and data caches have been replaced by instruction RAM and working RAM. DPUs are independent from each other's memory and run asynchronously. 16 threads can execute independently into each DPU, and all inter-DPU communications take place through the host CPU. This architecture allows each DPU to work efficiently on its own fragment of the dataset, and even with its own programming routine if chosen to be different. The technology comes with a set of tools that make the porting of applications as smooth as possible. DPU can be programmed in a familiar language and with standard tools and skills. UPMEM provides a complete software stack that enables DPU program to be written in C and APIs in common languages for host programming. Communication libraries make it easy to configure the DPU, organize the distribution of data, scheduling, and retrieve results. The compiler for the DPU target is based on LLVM and comes with some tools from the LLVM compilation toolchain. Applications are manifold. In genomics, we've ported a sequence alignment algorithm to UPMEM PIM, making it over 9 times faster than the traditional CPU implementation, while significantly reducing energy consumption. In the field of analytics, we have developed a proof of concept for an index search engine that runs nearly 30 times faster than the reference configuration. And we also developed a PIM extension for Apache Lucene, which will be detailed in a dedicated presentation this afternoon. For database operations, our PIM implementation of edge join is 9 times faster than the CPU version and much more energy efficient. In machine learning, our PIM implementation of k-means clustering outperforms both CPU and GPU in terms of speed and energy efficiency. Another example is our work on decision tree, for which we achieved over 40 times speed up with a significant reduction in energy consumption. As you can see, the potential for speed up and energy saving can vary significantly depending on the workload characteristics. In general, algorithms that are best suited to run on UPMEM PIM are those with highly parallel operations, those with irregular data access patterns, or those with algorithms that are difficult to vectorize. I'd like to mention UPMEM involvement in several key collaborative research projects supported by the European Commission and the French government. UPMEM is proud to be a beneficiary of the EIC Accelerator program, a mark of excellence that underscores our commitment to innovation. Among our flagships projects, BioPIM focuses on co-designing bioinformatics algorithms and data structures with PIM architectures with the long-term goal of bringing genomics to the point of care. SustainML is dedicated to developing a sustainable interactive framework for greener AI, prioritizing energy efficiency across the entire lifecycle of an application. Stratum aims to design an AI-centered tool for brain surgery guidance and diagnostics. Architas focuses on developing advanced AI accelerator for defense applications. And Odyssey aims to create a modular and energy-efficient edge computing system for AI, leveraging open source technologies and advanced accelerators. This project demonstrates UPMEM's strong partnerships and the significant impact of our technology across different domains. With a clear understanding of the technology and its applications, let's have a look to our technology roadmap. In May, we released a new generation of our PIM module. It features an increased frequency of 400 MHz or up to 40% lower power consumption at same frequency. It also introduces host access to the working RAM while the DPU on the bank, new monitoring features, and the ability to switch off DPUs, reducing idle consumptions by 90%. This new module will be detailed in the next presentation. Last year, we mentioned that we are starting to work on a roadmap for a dedicated chip for AI applications, including LLMs. Since then, we've made significant progress with our PIM AI design. This next generation chip is designed in a stacked configuration and is optimized for intensive AI operations with tensor and vector units. Early simulations have shown promising results in cloud and mobile environments. This PIM AI chip and the simulator will be detailed in a forthcoming presentation. Last year, we announced our transition to Ice Lake servers. However, we experienced some delays and are behind schedule. Despite their challenges, we are working to complete the transition and expect to ship these new servers by the end of the year. In parallel, we are exploring the potential of ARM many-core processors, focusing on ultra-ampere, as part of the Odyssey project. And in addition, we are going to work on other platforms yet to be defined as part of Stratum project. UPMEM Cloud has seen a substantial growth over the last year, with about 100 new active users and 15 new teams. We also logged around 10,000 additional hours of usage, highlighting the increasing engagement and reliance on our cloud service. As it continues to evolve, the new generation will be progressively deployed in the cloud servers. And last year, we announced plans to increase storage capacity and to offer dataset preloading options. While we experienced some delays, we remain committed to their announcement. Now that we've set the stage for the day, let me give you a quick overview of what's coming up. We will start with a keynote by Sylvain Brocard, who will present the hardware architecture and the intricacies of programming UPMEM PIM, detailing the features and announcements of the new generation and the latest version of the SDK. Next, Cristobal Ortega will present PIM-AI, the next generation chip designed to meet the needs of large language models. Throughout the day, we'll also have a series of research project presentations covering simulation, virtualization, programmability, index search engine, recommendation system, genomics, and homomorphic encryption. With that overview in mind, let's move on to our first keynote, and please join me in welcoming Sylvain.